Greetings to all my tech heads out there in the KevTechify Nation, and if you're new here, welcome. In this episode, we're going to look at spanning tree protocol. We'll be discussing spanning tree protocol, STP recalculation, layer 2 loops, STP port roles, spanning tree root bridges, STP coth, and selecting the root bridge. This episode is part of my series on network security. I'm Kevin, here at KevTechify. Let's get this adventure started. Spanning tree protocol, also known as STP, is a loop prevention network protocol that allows for redundancy while creating a loop-free layer 2 environment. The specification of IEEE 802.1d is the original IEEE MAC bridging standard for STP. How the switches work at layer 2 is when we have redundancy, how they forward out data, it's possible that data could start looping around in here. And so it could continually loop around, causing congestion, using RAM, processor, and just slowing down your network in general. What spanning tree does is it realizes that this loop exists and it's going to shut down this connection. So it's going to stop this connection right there. When a link goes down in spanning tree goes through a recalculation process. Remember originally that trunk 2 here was shut down because spanning tree decided we're going to shut this down. But if this connection goes down here, backhoe cuts through your fiber, somebody unplugs a router, there's a hardware failure, something happens, this link goes down, spanning tree will see that that link goes down, it'll come back over here, it will re-enable this connection, and now traffic can still journey through the network. So spanning tree, dynamic protocol for creating that loop-free environment, but maintaining the redundancy that you've built into your system. Without spanning tree protocol enabled, layer 2 loops, they can form, causing broadcast, multicast, or unknown unicast frames to loop endlessly on your network. You have redundancy built in case one connection goes down, but layer 2, how they forward frames, your broadcast, multicast, and unknown unicast frames, they could form a loop and that data could travel endlessly there. Now, when a loop occurs, the MAC address table constantly changes. That switch is constantly changing it with all the updates from those broadcast forms, which results in MAC address database instability, so it becomes unstable. And then this can also give you high CPU utilization because it's always updating it. It's always constantly looking at where does MAC address come from, what is the best path to it, and it's always doing that. Broadcast frames here aren't the only type of frames that are affected by loops. Unknown unicast frames sent on a loop network can also result in duplicate frames arriving at a destination device. The spanning tree algorithm designates a single switch as the root bridge and uses it as the reference point for all other path calculations. Here, the root bridge is S1. So it went through the election process. S1 is our root bridge, and it's chosen through an election process. All switches that participate in spanning tree exchange BPDU frames to determine which switch has the lowest bridge ID, a BID. So whichever switch has the lowest bridge ID automatically becomes the root bridge for that spanning tree algorithm calculations. When spanning tree algorithm has determined which paths are the most desirable relative to each switch, it assigns ports roles to the participating switch ports. The spanning tree protocol port roles are alternate, root, and designated. The alternate STP port role, or also known as a backup ports, they're configured to be in a blocking state to prevent those loops. And so right here, this alternate port right here, this is going to be blocking. So it's blocking traffic going in and out of it. So data is not going in and out. Alternate ports are selected only on trunk links where neither end is a root port. And so notice that neither end of this connection here is a root port. Now, what a root port is, and here's an example of a root port. We have two root ports in our spanning tree. A root port are switch ports that are closest to the root bridge. And so if we look here, on this switch on S3, which port is closest to the root bridge? That gives us our root port. So on switch 3, that's Fast Ethernet 01, that's directly connected to the root bridge. Down here on S2, the root port here is this port that's directly connected to S1. So this here, F01, is the closest port to our root bridge. So those are our two root bridges. Then we have our designated ports. So in our diagram here, we have 3 designated ports. If one end of a trunk is a root port, then the other end is a designated port. So if one end here is a root port, once again, root ports are determined, there's one root port per switch. The root port is the closest port to the root bridge. And so if one end is a root port, then the other end is the designated. Because this is the root here, this makes this other end of this connection a designated port. All ports on the root bridge are designated ports. That's the other thing. All ports here on the root are designated ports. So that's how we decide who's a alternate port, designated port, or root port. If you like this episode on spanning tree protocol and you get value out of it, and depending upon the platform you're using, please click that like button, give a 5-star rating, leave a comment, subscribe to my channel. Doing this supports the channel, which in turn helps me bring you more great content. You can also visit my website at KevTechify.com for all of my details on how to get these episodes in video and podcast form. Every spanning tree instance, whether it's a switch land or broadcast domain, has a switch designated as the root bridge. The root bridge here serves as the reference point for all spanning tree calculations to determine which redundant paths to block. An election process here determines which switch becomes the root bridge. After the switch boots, it begins to send out BPDU frames every 2 seconds. Now, these BPDU frames contain the switch bridge identifier, BID, and the root ID. Eventually, the switch with the lowest BID ends up being identified as the root bridge for the spanning tree instance. Here in our diagram, we can look here and see that each one of these has a bridge ID. So the priority here is 32,769, 24,577, and 32,769. The lowest bridge ID became the root bridge. So 24,577, lowest bridge ID on S1. S1 then became our root bridge. The path information is determined by summing up the individual port costs along the path from the destination to the root bridge. Each destination is actually a switch port. The default port costs are listed in this table. And we can see here that by the link speed and name here, so on a 10 megabit link, the cost here is 100 on the revised. So because of networks getting faster and faster, when they originally did these costs for spanning tree, we started off with 10 megs being a cost of 100 megs being 10, and then gig was 1. The lower the score, the better for this process. And then they came out with 10 gigs. Well, they had to have full integers, so they gave it a cost of 1. 10 gigs versus 1 gig. 10 gigs is definitely faster, so you wanted to do that. What they had to do was go back and revise them. And so they went back and they revised them, and that's what we get where we have the revised IEEE. And so 100 megs 10 megs is 100, 100 megs is 19, 1 gig is 4, 10 gig is 2. Now, the default port costs are defined by the speed at which that port operates. Now, to configure these port costs on an interface, we can enter in the spanning tree cost value. And the value can be between 1 and 200 million. The chart here is the default automatic values. You can override these. For some reason you wanted to have a higher value, you can give these paths, these links, a higher speed. Now, to verify the port and path cost to the root bridge, we can enter the show spanning tree on your switch, and it'll list out the path to get to the root bridge. When an administrator wants a specific switch to become a root bridge, the root bridge value must be adjusted to ensure that it's lower than the root bridge priorities of all the other switches on the network. There are two different methods to configure the bridge priority value on Cisco switches. The first one here, to ensure that the switch has the lowest bridge priority, we use the spanning tree VLAN ID root primary command in global configuration mode. Now, if an alternate root bridge is desired, we would use the spanning tree VLAN ID root secondary. So we are specifying which switch we want to be the primary regardless of any elections. Now, another method here would be to configure the bridge priority value, so that BID, using the spanning tree VLAN ID priority value. And this command gives more granular control over that bridge priority value. The priority value is configured in increments of 4096, and it's between the numbers of 0 and 61,440. So it has to be in increments of 4096, and it's between the numbers of 0 and 61,440. It was my pleasure to provide you with this wonderful episode on spanning tree protocol. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com, and you can get all these episodes in video and podcast form. In the upper right is my playlist for my series on network security. In the bottom right is one of my videos I think you'll really like. Thank you so much for watching this episode of my series on network security. Once again, I'm Kevin. This here is KevTechify. I'll see you next time for another great adventure.